Hello, everybody. Today we're going to revisit a concept that we really liked, was important for us, which is mapping reductions. But instead of the standard mapping reductions, we're going to talk about polynomial time mapping reductions. And this will play an even larger role in the chapter on efficiency than mapping reductions played in the chapter on computability. Today we're just going to see the definition and a little bit of what you can do with it, why is it useful. We'll see various examples of polynomial time reductions in two videos, but this definition will actually be important here, even to define this notion of NP completeness that will be the topic of the next video. So today, we're just going to define what are these polynomial time reductions. So polynomial time reduction is first a reduction. So we want a function that would transfer an input for one problem to an input for the other. But now we will insist that this function will be computable in polynomial time. So a function f is a polynomial time computable function if there is a polynomial time Turing machine M that on every input w halts with just f of w on its tape. So if M starts with w on the tape, when it halts, it has f of w on the tape. This part is exactly like what we had for mapping reduction in general. So this is just a computable function. But here we want this Turing machine to run in polynomial time. So there should be some c such that this machine runs in time bounded by n to the c for any input length n. And now we can define that the language A is polynomial time reducible to a language B. And we will write it as A smaller equal PB to indicate that it is a polynomial time reduction just rather than just any mapping reduction. If there is a polynomial time computable function f, so that w is in A if and only if f of w is in B. So now the three ingredients we need to prove for f to be convinced that it is a polynomial time reduction from A to B are first, that f is polynomial time computable, and then that if w is in A, it implies that f of w is in B, and if w is not in A, it implies that f of w is not in B. F is called a polynomial time reduction from A to B. And note that this means that there is some k such that this reduction is computable in time at most n to the k. And this in particular means that the output that you get is not too long. So f of w is bounded by the length of w to the k. It's not enough that the output is bounded, but this is one of the things we can conclude. We can conclude that the output length is bounded, polynomially bounded. So here is the picture. The picture is that we have a function, again, reducing from the domain of A to the domain of B. And if you're in A, f of w is in B. And if it's not, then it's not. And in addition, that on input of length n, you get output of length at most n to the c. Again, it's not sufficient, but this is part of what we can conclude. In addition, we need this computation to be to take time, which is bounded by n to the c. So f converts any string w into a string f of w, such that to decide if W is in A, it's enough to decide if f of W is in B. We reduce the problem of deciding if W is in A to the problem of deciding if f of W is in B. Here too, we have this nice transitivity property. If A is polynomial time reducible to B and B is polynomial time reducible to C, then A is polynomial time reducible to C. The reduction is just as before. You compose F with G. You first apply F and then you apply G. And here we need to also make sure that the computation is polynomial time. And it is because first F, you apply F, and this is a polynomial time computation. And then you apply G on an input which is polynomially bounded. And therefore, it will be polynomially bounded computation as well. And in particular, it means that the length of the output is at most some n to the CD. And so here we use the fact that because the reduction is polynomially bounded, then the outputs are also polynomially bounded. This is also where we're using the robustness of this notion of polynomial time. Polynomial time, we said it is robust to changing the model of computation. It's also robust to these kind of operations like composition. If you apply two polynomial time computations, one after the other, then what you get is polynomial time. This is not correct necessarily if we thought about quadratic time as a specific notion of efficiency. And now we can conclude a few important properties. If A is polynomial time reducible to B and B is in P, then A is in P. Because how would you solve A? You'll first in polynomial time reduce it to B, and then in polynomial time you'll decide if f of W is in B, and this will give you an answer about A. So let MB be a polynomial time Turing machine that decides B. Let F be a polynomial time reduction from A to B. We build a machine MA that decides A as follows. On input W, you first compute f of W, which is polynomial time. And then you run MB on f of W, which is again polynomial time. And you output the answer. And the answer is correct because f of W is in B if and only if f of W is in A. Similarly, if A is polynomial time reducible to B and B is in NP, then A is in NP, the same kind of proof would work. So it's very analogous. And these two reductions are the algorithmic side of reductions. And if we have the algorithmic side, we can also have the more complexity theoretic side, the impossibility side. In particular, if A is polynomial time reducible to B, and A is not in P, then B is not in P. And with that, we conclude this short video. So we've seen the return of mapping reductions. As I said, this course, this reductions in general is the one technique we are going to use over and over. But this time, the reductions also include an efficiency constraint. We saw algorithmically how to use it to show membership in P and in NP. In complexity, it will play a major role, for example, to show that something is not in an P, as we kind of argued before, but we'll actually see that it plays a much more major role through this notion of NP completeness that we will see in the next video.